Hey guys, welcome back to the Spacecraft Design Engineering course. This is lecture number 3 of the course, and so yeah, let's get started. So once again, if you don't know, my name is Shushanth, and I'm going to be your instructor for this course. Alright, so let's go through the objectives. So in this lecture, we plan on going through the overview of common propellants utilized in rockets. We're going to go over solid rocket boosters and how they work, and we're going to go into pressure-fed systems, monoprop, biprop, and cold gas thrusters. And we'll go into the other engine cycles in a future video. So let's start with rocket propellants. So liquid fuel rockets typically use a variety of propellants, and there are a few common propellants utilized in the modern day. So we have a few sections or types of rocket fuels. So first we have cryogenics. The most common ones right now are liquid hydrogen, liquid oxygen, also known as hydrolox, liquid methane and oxygen, which is also known as methalox, and liquid kerosene and oxygen, or RP1 and oxygen, which is known as kerolox. And so right here on the left side, you'll see a few pictures. So on the left part of this chart, you see the Space Shuttle main engine, the RS-25, which runs on a mixture of hydrogen and oxygen. This reaction primarily produces water vapor, which is the reason why you see basically a clear and bluish flame. Whereas on the right, you see liquid kerosene and oxygen. We have RP1 and oxygen on the F1 engines of the Saturn V, and that has a reddish orangish color. So basically, the exhaust byproducts will determine the color of the plume, and it depends on whether you're using cryogenics, solid fuels, or hypergolics as well. So let's go move on to hypergolics. So the most common fuels, there's a variety of fuels used for hypergolics. The fuels itself are Aerozine 50, MMH, and UDMH. And the most common oxidizer for these fuels is nitrogen tetroxide, or NTO. And lastly, we have solid fuels, which we're going to get into on the next slide. Alright, so solid rocket motors. So these rockets typically rely on solid propellants that are composed of a fuel and oxidizer. They're mixed together preliminarily, so they don't have to mix inside a combustion chamber in order for the reaction to occur. So typically, a material called P-band is used as propellant within modern solid rocket boosters, like the ones you see on the Space Launch System on the right, or the Space Shuttle back in 2011. And so how they work? Well, there's actually an igniter at the top of the stack. So around here, with the forward segment, there's going to be a small solid rocket motor or some kind of explosive that ignites the whole stack, and it ignites from top to bottom on launch. And so this reaction is converted to viable thrust, and which depends on the surface area the propellant that the combustion is exposed to. So basically, solid rocket motors start the propellant burning around like this diameter, and eventually as the fuel depletes, it starts going outward and outward and outward. And so that starts to increase the surface area, which could impact the thrust curves. So engineers have to find different workarounds by changing the surface area to control thrust. So here we have an example on the left of the multiple surface areas that you can create within these solid rocket motors. So right here on option number 2, we have a circular grain, propellant grain. That's what that's called. The correct term for it is called. And so it's going to burn outward, and the center part's going to burn inward as well. Right here we have a star, we have another shape right here, and then we have this odd shape right here. And as you can see, all of them have different thrust curves as the time increases. So, for example, this one has a roughly constant thrust for most of the time, and then it starts going off into at this point right here. And all these are unique, and so that's the beauty of solid rocket motors. Even though you can't turn them off or control their thrust, you can control their thrust actively. You can passively control their thrust by modifying the surface area. And so right here on the right, we have the AJ260, which was a solid rocket booster the largest solid rocket booster tested as of yet. It was planned to be used for the Apollo program for taking humans to Mars, but as that project was scrapped, this solid rocket motor is no longer in use or development. Okay, so now let's move on to pressure systems. Pressure fed systems, sorry. So one thing we got to know, pressure always flows from high to low. That's just a fundamental in physics, a fundamental feature in physics, right? So if you have a high pressure tank flowing into a lower pressure environment, that gas will accelerate out of the nozzle. So usually this propellant is found in high pressure tanks called COPVs, or composite overwrap pressure vessels. So usually they're pressurized hundreds and hundreds of bar. And so there's going to be a valve like around here in this image. And that valve, once that opens, all that pressurized propellant leaves the nozzle. And this is what's called a cold gas thruster. It's the simplest kind of pressure fed system, which uses inert gases, usually like nitrogen, to generate thrust. And yeah, so this reaction, once again, exerts an equal and opposite force on the rocket itself. So that's the action-reaction pair that we were talking about in the previous lecture. And so yeah, this is the basis of most monopropellant and bipropellant thrusters, and which we'll get into in a minute. Okay, so now we know the basis of the most pressure-fed systems. We know how a cold gas thruster works. But what if you want to increase the efficiency, or the delta V of your system? Well, you can increase delta V by increasing the exhaust velocity, or the energy released through a chemical reaction, which is exactly what these kinds of thrusters do. So monopropellant thrusters rely on a single fuel tank that's pressurized by helium from another tank. So the propellant, once the propellant is flowing into the nozzle when the valve opens, it's going to react with a catalyst that speeds up a reaction and produces viable thrust. So most of the time you get things like iridium as a catalyst with a fuel composed of hydrazine. And so these thrusters are utilized on the Boeing Starliner and other orbital spacecraft. Bipropellant thrusters are composed of two propellants, pressurized by two accompanying helium spheres. And I'll show you what I mean by helium spheres and pressurized tanks. So right here, this is one of the space shuttle's orbital maneuvering system pods. This right here is an AJ-10, and it is a bipropellant thruster. So for a monopropellant engine, this sphere right here would be filled with helium, and this tank would be composed of the fuel. So as the fuel depletes, the tank is going to be pressurized from helium from this sphere. But in a bipropellant system, what you have is two different propellants with two helium spheres. And so these propellants are going to be injected into a combustion chamber for a much larger yield of energy compared to your average monoprop thruster. So yeah, they rely on a chemical reaction between the two fuels. And an example in the modern day would be monomethylhydrazine and nitrogen tetroxide as the oxidizer. So this is what was used on the shuttle. All right, so looking at this right here, here we have on the right another model of a bipropellant thruster just to make it easier to see. So we have two pressurants, which are usually going to be helium. We have a fuel, we have an oxidizer, and these are going to react together in a combustion chamber and are going to be expelled out of a nozzle. And here we have a monopropellant engine, which has a chemical or fuel flowing in, and there's going to be a lower catalyst bed and an upper catalyst bed. This is where the nitrogen tetroxide is going to react and get expelled out of the nozzle. Typically, bipropellant engines have a higher specific impulse due to the higher energy contents that you get when you're reacting a fuel and an oxidizer together. Okay, so that pretty much sums it up for this lecture. In the next lecture, we're going to delve into more complex propulsion technologies that do not rely on pressure-fed systems. So this will include things like open cycle and closed cycle combustion engines that are going to be much more complex than the average Boss pressure fed system. So here are two examples. We have the Merlin engine and the Raptor engine. So I'll explain exactly how some of these engines work in the future. This right here, just for preliminary knowledge, is an open cycle engine. This right here is a full flow staged combustion cycle, one of the most complex engines ever made. So yeah, that sums it up. Thank you guys for listening, and we'll see you in the next lecture.